So in this section or chapter of the Laplace transformation, we're going to learn a different approach to solving differential equations using a new technique that will involve something called an integral transform. Now, to preface this entire chapter, this technique is very interesting in that a lot of the differential equations that we know right now, this technique is overkill. Like you would not want to solve any differential equation using this technique because this is kind of designed for more complicated problems, especially when you're talking about the fields of like electrical and anything with signals and systems, because you start to run into weird functions that are very hard to describe with nice functions. So when you run into those types of problems and trying to solve them using our traditional techniques of the auxiliary equation, they don't really work well. But if you kind of go beyond that and we start to think like, okay, are there different approaches? This is one of them. So in the beginning, it will not feel satisfying in the sense of like, I feel like I'm doing a lot of work to solve an easy differential equation, but it's just not attacking the right problem, just because those kind of problems are much more difficult, and this class just doesn't have the time to cover them. So you have to keep that in mind. Like this technique has value. It's just what we're covering in this class isn't the best showcase of that technique. So always keep that in mind. So to begin with the integral, sorry, the Laplace transformation, we're going to have to use improper integrals a lot. So let's just review what that is. So an improper integral. An improper integral is just a integral with infinity, right? So if your bound contains infinity, it is improper. We're mostly going to go to positive infinity. In fact, we're only going to go to positive infinity for the Laplace transformation. So the integral that we're going to be working with will look like this. And the easy strategy we have come to know, like in Calc 2, I believe, is we take the limit as we approach infinity of the integral, like this. And if you're wondering, why do I take the limit? Like, what is the purpose? Well, the reason is the fundamental theorem of calculus says that you can find the area under the curve or the antiderivative, or sorry, the integral by taking the difference of the antiderivatives at b and a, right? So the problem is the definition, sorry, the theorem of the fundamental theorem of calculus requires that a and b be a closed boundary. However, infinity can't be closed because it's not a number. It's some object that just never ends, right? But taking a limit allows us to close that boundary, essentially, and make it finite, but not actually make it finite, where essentially I satisfy the conditions of the fundamental theorem of calculus, and I can basically do this now. So that's kind of the whole reason we do this limit approach is just because without it, that equal sign after the integral wouldn't be logical. So this right here is so that I can use the fundamental theorem of calculus. Like that's the whole reason we take the limit. It's just so I can satisfy the theorem. So if the limit exists, we say the integral converges. If it doesn't exist, it diverges. So all of our integral transforms are going to be improper integrals, so it's just not a bad idea to remember how to take one of these, right? So we're going to do one, very simple one. So the integral from 1 to infinity of 1 over t dt, right? So the first step we would do is we would write it as a limit. So the limit as t approaches infinity of the integral from a to b, it's not a anymore, it's 1 over t dt, which we know the integral of 1 over t is the ln, right? It would be the ln of the absolute value of t, but because the boundaries are 1 to infinity, i.e. positive numbers, I don't need them. Can't forget to write the limit. And then we're going from 1 to b, and then we plug in b, so the limit as t approaches infinity of the ln of t. Now, the limit of a constant is just the constant value, so I actually don't need the limit on the second term, just because, again, the limit of a constant is the constant. The ln of 1 becomes 0. That's just what is by definition. And then I get the ln of infinity, which is equal to infinity, which means it diverges, right? So that's just how you take an improper integral. You take it normally, but you just deal with infinity later, right? We have to do this whole limit thing to make it proper. Now, to be clear, if you're doing like a homework problem, do you need to write the limit down? Not really. Like if you're not doing something formal, that you can kind of treat infinity as a number, although I never said that. But if you're doing a proper, demonstration of this, you should carry the limit everywhere until you finally use it. So we're going to need this because Laplace transformation is built on this integral type. So now we got to define a special type of function that's going to be very common in the realm of Laplace transformation, and that's going to be a piecewise continuous function. So a function is said to be piecewise continuous. Now, this definition, it's going to be a little bit weird, but just take it piece by piece. So it's piecewise continuous on AB if the interval can be partitioned by a finite number of points such that, so we have two things, f is continuous on these partitions, and then f approaches a finite limit at the endpoints. The endpoints of the partition. So, a pretty common type of signal that you would deal with in like electrical engineering circuits, something like that, right? Is what we call a sawtooth signal, right? It goes up and then down, up and then down, up and then down, right? Like this is what we call sawtooth because you kept drawing, it looks like a sawtooth, like a saw. There's other ones like a square one where it's like, this, right? Square waves. So you can do all kinds of interesting waves. So the problem with this function is there's these jump discontinuities, right? So where those dashed lines are, these are jump discontinuities, right? Jump discontinuities. And we know that at those points, the derivative does not exist. They are not continuous. So there's a lot of issues with those points. However, everywhere else, they're perfectly fine. They're nice, continuous, linear lines. So piecewise continuous just says, what if I could ignore those points and just focus on the part that is continuous? That's the behavior that's more interesting. So that's what this definition is saying is that rather than me defining continuous, I am defining a different type of continuous that's useful to me to analyze very interesting problems. And that's all it's saying. The second part where it approaches a finite limit, if I take the limit from the left side, I get to this number. If I take the limit from the right side, I get to this number. So they always go to a number. What they're trying to avoid is like a situation where you have something like this, right? Like they don't want this because then that's kind of annoying to deal with, right? Because then you have this infinity limit and it just makes things like, well, how do I know it's continuous at infinity? I don't. It's just because it goes forever, right? Here I do know it's continuous everywhere. That's not the endpoint that I have to jump over essentially. So that's the whole point. Again, this is just something that's going to come up a lot in these types of problems, and that's why we define it. Because one of the strengths of the Laplace transformation is analyzing signals. Like that's really why we like it, because it's very good at analyzing signals. So now we're going to get into what the Laplace transformation is and where it comes from, essentially. So, a useful tool to solve differential equations um, with these types of behavior is called the integral transform. Now, one of the things I get asked sometimes is like, where does this come from? Like, how would I have thought to do this? And the answer is always like, you probably wouldn't have. Like, this is just something that someone realized works, and they created it, and then people started adding to it. So I don't really have a good intuitive answer for like where it comes from, but there is this kind of like idea that you can kind of see from it if you like really look closely at what the form is. So what does an integral transform look like? Well, an integral transform is a relation of the form. So the basic principle is I have a variable, let's say t, and this variable t is fine, but where I'm located is it's just not working for me. Like it doesn't, like I can't really do anything with it. But I recognize that if I could transform my variable t or the domain I am in into another domain where things are nicer, could I do that? And the answer is yes. So how do I do that? Well, you just take an integral from a to b. You pick a special function that has two variables, s and t, right? Notice that they both have s and t. And then you multiply it by your function, whatever you're trying to transform, with it. And whenever you take the integral of a variable, that variable will disappear after you do a definite integral. So because my first function has s and t in it, and my actual function f of t is the one I'm using, the end result is I'm left with only the s variable, right? So I've transformed from a, say, a t domain to an s domain, right? Like that's kind of the whole principle of this is I'm going from one variable to another. Now, that function k is called the kernel function. Now, there's only going to be one kernel function in this class, it's the Laplace, but there's many of them, right? So this transformation, the transformation, takes you from the t domain to the s domain. Now, again, you might be asking the question like, why would I want to do that? Well, the answer is this. In one domain, things are ugly. Like if you go back to this example, in this domain, where this is t, it's not very nice to deal with. However, if you do a transformation into this S domain, it turns out that the picture, and this is not correct in the sense of like this is what it actually would look like in correctly. I'm just saying like this is the type of answer it would look like. It's going to become a sine and cosine curve. Notice the difference between these two curves. One has discontinuity, has issues with differentiability, but the one on the right, well, that's a nice curve. It's all smooth. Everything is continuous. Everything is differentiable. Like, that's what we like. And that's why we do it. Because I can analyze this problem in a different domain. Well, the question then becomes, well, if I do that, does everything I work on in the S domain carry back to the T domain? The answer is yes, it does. And that's through the inverse Laplace, which is going to be in 6.2. So that's why we do this. It's just to get into a nicer domain. If you've taken linear algebra, there's a section called change of coordinates. This is essentially the same thing. You're just changing the coordinates of your function into something else to work with, and then you'll eventually come back. In Calc 3, you do the same thing with polar transformations or cylindrical coordinates, right? In one domain, the integral is impossible, like e to the x squared plus y squared, right? If you try to take that integral, you can't. It's impossible. We don't have an antiderivative that works. But if you convert it to polar, then it just becomes this. And that's just a basic U sub. In one domain, impossible. In the other domain, it's an easy U sub problem. That's essentially what we're doing. We're just making our life easier. Now, the process of the conversion itself sometimes isn't easy, but the alternative is I can't solve the problem, right? So like that's kind of the trade-off you have to ask yourself. So what's the kernel function we're going to work with? Well, it's going to be this one. So for the differential equations we are observing, um, the kernel function will be an exponential function, which is kind of nice because it's not a difficult function to deal with. E to the negative st, where we will assume that t is greater than or equal to 0 for Laplace. If I remember correctly, I believe Fourier assumes that t can be negative infinity as well. But for Laplace, it's going to be positive infinity. And just to show you, there are many kernel functions, and you don't have to memorize any of these. This is more of just like a intellectual curiosity. But if you look here, there are many, many different kernel functions. And the most common ones that you would see are the Fourier transform, right here, and then the Laplace transform. All of these transformations are just useful for a specific problem, right? So whichever one you use just ends up being, well, what problem am I trying to solve? So that's kind of their value. So that is the Laplace transformation. So now we will actually find the Laplace transformation and kind of set up the notation. So let's define it. Definition. Let f be a function defined for f of t, sorry, not for f of t, for t greater than 0. The integral f of s equal to the integral from 0 to infinity e to the negative st f of t dt is the Laplace transformation because I'm going to use this word so much, I will abbreviate it as LT. So if you ever see LT, that just means Laplace transformation. If the integral converges. And then our notation. So if you see f of s, you will also see it sometimes written as this curvy little L. And then we use curly brackets. So most people will use curly brackets. So you'll get good practice making these. There we go. Laplace transformation of s, like that. So that's our notation that we are going to use. So now we're going to do an example of taking the Laplace transformation just so we can see it. So I'm going to skip to the Laplace transformation of t just because we're going to have to do integration by parts and it's always good to review it. So the Laplace transformation of t, right? So step one. Now, one thing to note when you're doing this, this is kind of like when you learn like the limit definition of a derivative, right? Or Riemann sums. In practice, you're not going to be taking these integrals. However, in order for us to be able to skip to like using the tables, we kind of have to do this just to gain appreciation. So in the long run, you will not be taking these integrals. You might have a problem or two where they say use the definition of Laplace transformation to find the answer. But at the end of the day, you can use the tables, right? But we should do one or two just to gain some appreciation for it. So step one is formula. So the integral from sorry, not a, it's 0 to infinity, e to the negative st f of t dt. To be clear, these are all s's, not fives. So my s's look like fives, unfortunately, and I tried to pick problems without any fives, but I will try to make them as distinguishable as possible. Step two, plug in. So f of s is equal to the integral from 0 to infinity, e to the negative st times t dt. Step three, limit. The limit as t approaches infinity of 0 to b e to the negative st dt, except it's a t. Step four, integrate. So this is an integration by parts. So in case you forgot how to do that, remember, we're just going to set up what I call like a table. So u is equal to, actually, I should say it right here. U is equal to some function, and then dv is equal to another function. I'm going to take the derivative of u, and I'm going to integrate dv. So u should not get worse, and dv should hopefully not get worse either. So the function that doesn't get worse when you take a derivative is a polynomial. So when you take the derivative of t, you get 1 dt, right? And then if you integrate e to the negative st, s is a constant. So s is treated as a constant because we're integrating with respect to t, not s. So then the integral would be e to the negative st over negative s, like that. And don't forget dt on this one. Now, if you're wondering, why is it 1 over negative s? It's because the integral of e to some constant times t is just 1 over that constant, right? In case you forgot, e to the kt dt is 1 over k e to the kt. Just as a reminder. So the integral then becomes the limit as t approaches infinity of u times v, so that times that, minus the integral, well, I need a limit still, and it's not t goes to infinity, sorry, it's b. Just realized that. Of 0 to b of negative 1 over s e to the negative st times dt, like that. Okay, render uv minus integral v du. That's integration by parts. The way I memorize it is I do the diagonal product minus the product of the bottom one. That's how I've memorized it. And then if I integrate this, right, and this should be 0 to b. So I'm going to plug in b minus 0 e to the negative s times 0 over negative s minus the integral of e to the negative st is again just e to the negative st. So minus, let's see, 1 over negative s e. Well, can't forget the limit. Sorry. The most frustrating thing about these is going to be your signs. So 1 over negative s, e to the negative st over negative s from 0 to b, right? That's just the integral. And then if you evaluate this one right here, you are going to get, so reminder, because it's going to come up, e to the negative infinity is equal to 0. So that's another important one. So we get b e to the negative infinity. Sorry, not e to the negative infinity. S times infinity over negative s. And then we just get 0, because anything times 0 is 0. And then here, we're going to get 1 over s squared, e to the negative s t, I guess b, but now we plugged in infinity, minus, now this is where a bunch of negative signs come into play, so we have double negative there, so 1 over minus squared, negative s times 0, like that. Now, here's the thing. Depending on what s is, it will either create a divergent solution or a convergent solution. So if s is negative, right? If s were negative, then check this out. If s were negative, then I would get a negative negative, which is positive, which would give me positive infinity. So if s is less than 0, it diverges, which is why you'll see this a lot when you're doing these. They will state that s has to be greater than 0 or a specific number for it to be convergent. So s is greater than 0. So if s is greater than 0, then what I end up getting is 0 minus 0 minus 0 minus 1 over s squared. Now, if you're wondering what happened to the e to the negative s times 0, e to the 0, as always, is equal to 1. So this right here becomes e to the 0, which is equal to 1. And so then I get that. And then a negative negative becomes 1 over s squared. And that's our answer. So that's how we get 1 over s squared. And that's the integration style of taking the Laplace transformation. Again, are you going to do this a lot? No, you're not going to do this a lot. But they might ask you like one question, right? How do I make this more difficult? I could actually tell you to do it for a time domain that doesn't start at 0. So I could say, hey, find the Laplace transformation given t is greater than 1, right? So instead of me starting at 0, I am just telling you, hey, can you start at 1 instead, right? Well, how does that change? It just changes the boundary. So step 1, formula, instead of it being 0 to infinity, it would be 1 to infinity uh, e to the negative st times f of t dt. Step 2, plug in. So f of s is equal to 1 to infinity e to the negative st times 1 dt. And then step 3 would be to do the limit. So the limit as b approaches infinity of 1 to b e to the negative st dt. Step 4 is to integrate. Not an improper, sorry, not a integration by part. This is just a generic integral. So e to the negative st becomes e to the negative st divided by negative s from 1 to b. And here I end up getting e to the negative s times infinity over negative s minus e to the negative s times 1 over negative s, like that. And then assuming that s is greater than 0, because otherwise we would get a divergent solution, we get 0 minus e to the negative s over negative s, which is equal to e to the negative s over s. And that's our answer. So that's all that happens is we just get a slightly different answer, but it's no different. It's just a different integral boundary. That's all. So if you're wondering, what are some important integral transformations that I will need to know in the long run? I'll give you a table here of Laplace transformations. These are some pretty big ones, okay? Definitely the first three are huge. Like you're going to do those all the time. And then sine and cosine, those are pretty big too. The other ones that are there, they might come up on a homework problem, but I'm just telling you, like the one through three and seven and eight, those are massive. Like you're going to do those all the time. Um, this little function right here that they mentioned, there's one homework question, I believe. This is called the gamma function. It's just an interesting formula to deal with combinations and permutations, I should say. Not something that's like really important for this class, but again, they might be one homework question where you have to just use it as an answer. So it's just a generalization of number three. So from here on out, we're not going to do integration anymore. We're just going to use our table to match it up and then reverse engineer it essentially. So something interesting about the Laplace transformation that you have been exposed to. If you've taken linear algebra, you've already talked about this idea. But if you've not taken linear algebra, you've maybe heard about it, or you've definitely worked with the concept because you know how to take derivatives and integrals. And that's the idea of a linear transformation. So properties of Laplace transformation. So the whole value out of doing the Laplace transformation is that we can go from one bad domain to another, sorry, to a good domain, and then eventually work backwards, right? And the reason that we're able to do this in a very nice way is the idea of linear transformation. So um, the Laplace transformation has two properties that are special, which are number one, if you take the Laplace transformation of two functions added together, you can take the Laplace transformation individually and then combine them later, right? Another thing that you have done with this is your derivatives, right? The sum difference rule. Like that's a property of differentiation. Same thing with integration. And that's an important property because what it means is I don't have to have fancy formulas for multiple functions being added together. I can just break them apart and work on it one by one, kind of like superposition, right? And the second property says if you take the Laplace transformation of a constant times a function, you can just take that constant right outside. It doesn't affect the transformation, and it's essentially our constant multiple rule for differentiation. So these two properties make it a linear transformation. So the Laplace transformation is a linear transformation. So very nice property to have. And if we're dealing with functions that go from reals to reals, it's also called a linear operator. Linear operator just means the same domain and same codomain or range, really. So you might hear that word too from time to time. If f of t and g of t have the same domain and codomain, it is a linear operator. For you in this class, it's not going to be, it doesn't matter. It's just you might hear that word and I want you to know what it means. It just means they have the same domain and codomain. The outputs and the inputs have the same structure essentially. So now we want to be able to take the linear transformation of just a random function, but not through integration, rather using that table that has been provided. So that's going to be our next example is, okay, now let's take the Laplace transformation of a function. Now, just like integration, you don't have to show every single step. You kind of just do a lot of it in your head. But in the beginning, let's just kind of practice the whole structure of it so we can kind of understand, okay, that's what we're doing, right? So step number one is identify useful transformations from table. So we notice that everything is a polynomial, t to the nth power. So then that tells us that we're probably going to use this one. We're going to be using this transformation, right? So that's good to know. Okay, now we're going to use properties. Again, in the long run, you're not going to be doing this. You're just going to go straight into it. So the Laplace transformation becomes 3t to the fourth power plus the Laplace transformation of 7t cubed, 7 times t, not 70, plus 8, sorry, I forgot the Laplace, t squared, plus the Laplace transformation of minus 1. I always put the negative inside. It's just personal habit. Now, you can factor out the constants. Again, you don't have to do this, but we're just seeing how all of these properties interplay with each other. And then notice, right? I have 1. I don't see 1 doesn't really work for t to the n, but the Laplace transformation of 1 is just 1 over s, right? So that's another useful one. So then we just use our formula. 3 t to the fourth power becomes 4 exclamation point s to the 4 plus 1 plus 7 3 exclamation point s to the 3 plus 1 plus 8 2 exclamation point s to the 2 plus 1 and then minus 1 over s. And that's the answer. We can simplify this if we desire to. So the question is like, what is that exclamation point? I didn't tell you what it was, but it's called the factorial. So 5 factorial, that's how you say it, would be 5 times 4 times 3 times 2 times 1, which I believe is 120. That's all it's saying, is you're just multiplying the first number that you see with the exclamation point, and then you just go down by 1. So n factorial is just equal to n times n minus 1 times n minus 2 dot 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 3, 2, 1. If you're wondering, where does that come from? It's called permutations. So here's an example. Imagine you have a bookshelf and you want to organize 5 books on the bookshelf, assuming that number one, a book can't be in 2 spots at the same time because that doesn't make sense, and that every book is unique, right? How many ways can I pick the first book to put it into the shelf? I have 5 options. How many ways can I pick the next book now that I've already used the book? Well, I have 4 options. And then 3 options, 2 options, 1 options. And then there's this fundamental multiplication rule with counting, where you could just multiply all the different outcomes and you get the total number of ways of organizing 5 books on a shelf. Now, mathematicians came up with the shorthand notation to not have to write 5 times 4 times 3 times 2 times 1. That's where the exclamation point comes to play. It's the factorial. Your calculator is capable of computing this. They all usually have that button. So if you do the calculations, 4 factorial times 3 is 72. S to the 5th power, again, sorry, with the S and the 5, plus 42 over S to the 4th power, plus 16 over S cubed, minus 1 over S. Also, not going to come up, a 0 factorial by definition is 1. That sounds about right. So just something to think about. I got to make sure about the 0 factorial. It's been a while since I've done a specific one for some reason. Yeah, it's 1. Like it makes sense in my head that it should be 1. But yeah, that's how you do a Laplace transformation. let's do another example now with sine and cosine, because sine and cosine can be a little bit trickier. The Laplace transformation of sine of 4t plus cosine of 4 times t. So step number one is going to be, what did I say over here? Look at table. So I see sine and cosine. So then sine of some number, what do we use, a or t? We use a. So sine of at is going to be a over s squared plus s squared. Sorry, s, no, a. So one thing about sine and cosine is they look very similar. So make sure that you do not confuse them because it's very easy to do that. Sine has a on the numerator, cosine has s on the numerator, like that. So that is the table that we're going to, formula we're going to be using. All right, step two, Laplace transformation. So the Laplace transformation of sine of 4 times t plus the Laplace transformation of cosine of 4t is going to be equal to, so you need to identify what a is, right? So you notice that a is right here. So um, we get 4 over s squared plus 4 squared plus s over s squared plus 4 squared, which is equal to 4 over s squared plus 16 plus s over s squared plus 16. Notice that they have a common denominator, so very often you will see something like this, 4 plus s over s squared plus 16. And there you go. That's how you do cosine and sine. So now let's do one with the exponential. The Laplace transformation of 8e to the 4 times t. So again, step number one is look at the table. If we look at the table, we notice that e to the at is 1 over s minus a. So e to the at is 1 over s minus a. So now we have our formula. Step two, Laplace transform. So we can factor out the 8. You don't have to, but you can. Again, your goal in doing this is just to make it look like something on the table. So you have to manipulate it, which we just did. And then we get 8 times 1 over s minus 4. And so we get 8 over s minus 4. So that's how you deal with exponentials. And again, we can start mixing and matching them. We'll do another one here where we'll have to deal with the gamma function. But again, you're not going to use it beyond just writing it as an answer. So the Laplace transformation of, what is that? Let's do 8t to the 3/2 power. So step one is the table. We look at the table and we recognize that this is number 4. So we're going to use the gamma function. So number 4 says the Laplace transformation of t. What letter do they use here? They use n. And then for p, oh, sorry, p. Sorry, t to the p. Nope, let's just do this. Becomes the gamma function p plus 1 over s to the p plus 1. And then step 2 is Laplace transform. So Laplace transformation, I'm going to factor out the 8. t to the 3 halves. And then that's going to be equal to the gamma function times 3 halves plus 1 over s to the 3 halves plus 1, which if you wanted to simplify, you could write it as, I believe, 5/3 over s to the 5/3. And that's it. It's just one of those questions where you just got to know the formula. Now, an interesting thing that you'll have to be able to do with some of these problems is you're going to have to know properties of exponents. You're going to have to remember some trigonometric manipulations potentially. So just some quick, useful expressions. Sorry, useful algebra is a better way of saying this. Number one, x to the n, x to the m is equal to x to the n plus m. X to the m to the nth power is x to the mn. Just again as a reminder. Number three, sine squared x plus cosine squared x is equal to 1. Some double angles might come into play. So 2 sine x cosine x is equal to the sine of 2x, right? These are things that may come up and you might have to use them. So just as a forewarning. Now, let's do an interesting Laplace transformation. We can probably do it on the next slide, yeah. And this will come up much later, but this is an interesting one. The Laplace transformation of something like 4t cubed e to the 8t. Now, if you look at our table, you might be thinking, I don't have anything for that. Well, I only gave you a piece of the table. The table has like 20 plus functions on it, right? So you'll have a full table for you on the exam, right? So you will have a full table. And so if you look at your table, there's going to be one of them that looks very similar to this, right? And the table would say, if it's t to the nth power, e to the at, then the Laplace transformation is going to be n factorial over s minus a to the n plus 1, right? And just to make this more interesting, let's make it -8. So you see what happens when it's a negative number. So step two is to take the Laplace. So we'll take the Laplace transformation. So the Laplace transformation, we're going to take out the 4, and we get t to the third power, e to the -8t, right? And we notice that we have 3 and we have -8 right there. So that this is going to be equal to 4 times. So the factorial is going to be the exponent of the polynomial. So it's going to be 3 factorial over s minus -8 to the 3 plus 1, like that. And so what we end up getting is 3 factorial, 3 times 2, which is 6. And then times 4 is 24. And then we get s plus 8 to the 4th power. So if you ever see s plus a number in the denominator, that usually means the exponential is negative. The exponent of the exponential is negative. So we're going to do an example now with a special type of Laplace transformation. And again, it's just going to come down to you just knowing this formula. So let's do an example of it. Actually, let's just write the formula down. So formula. And again, this would be on the table. So the formula is going to be the Laplace transformation of some polynomial t to the nth power times any function f of t. So it's more of a generalized one. So if you imagine the exponential or sine and cosine, those are the most common applications of this. but this is for anything. This is going to be equal to, so it's an alternating sequence type problem. So there's a -1 to the n power. So it's either positive or negative, depending on the number of derivatives you're going to take. So you're going to have f of s, okay? But not just f of s, you're going to take the derivative of the Laplace transformation n times. So through an example, you'll kind of see what that means, right? So here's an example for you. Find the Laplace transformation of t squared sine of 8t, right? So step one is formula from table. And so we write down what we have up there. Then step two is identify f of t and n. So you want to know what those numbers are, okay? So we notice that this is to the second power right here. And so that means we are going to use n equals 2. And the f of t function is the non-polynomial part, so sine of 8t, like that. So what you're going to end up doing, and so this is kind of like the part that's a little bit tricky, is you're going to essentially take the linear transformation of f of t. So remember, by definition, okay, by definition, f of s is equal to the Laplace transformation of f of t. Like that's just how we define it. So t to the n power is not f of t. It's just a part of the form that lets us get into this shortcut, right? So step three is to take the Laplace transformation of f of t. No t to the n. So the Laplace transformation of sine of 8t, according to our table, is going to be, well, this is a, so it's going to be 8 over s squared plus 8 squared, right? That's our Laplace transformation. So this right here is equal to f of s, right? Step four, so according to my formula, I have to take the derivative of f of s n times. So I'm going to find f to the nth derivative using n equals 2. So that means I got to take one derivative, and unfortunately, this is not a fun derivative. It is a quotient rule. So the quotient rule says f prime g minus fg prime over g squared. You could do the chain rule using the property of exponents by bringing it up, but let's just do the product rule, so the quotient rule. So 0 minus the derivative of that. So derivative with respect to s is going to be 2s over s squared plus 8 squared, right? Actually, you know what? Just so that I don't lose people in that step. F prime g minus f g prime, like that, all over s squared plus 8 squared. You can write 64 if you want. So that's our first derivative. And so we get negative 16s over s squared plus 64 squared. And then I got to take the derivative again, right? And you can do the product rule yourself on the second one after seeing the first example. But if you do this correctly, you're going to get 16 times s, sorry, not s, 3 s squared minus 64 all over s squared plus 64 to the fourth power, right? Oh, I see what they did. I think they simplified it actually. Well, it's going to be cubed. because of simplification through the what's it called? Cancellation of an s squared plus 64 on both terms. So that's the second derivative. If you need to work it out, I recommend you work it out to convince yourself that's the answer. And so then step five is just going to be, okay, now we just use the formula. So step five is use formula. So the Laplace transformation of t squared sine of 8t is equal to negative 1 to the second power times 16 3s squared minus 64 all over s squared plus 64 to the third power. And then negative 1 squared is just positive. So we just get 16 times 3s squared minus 64 over s squared plus 64 to the third power. And that's it. That's how you deal with a problem like that. So the key thing that you have to recognize is f of s just means Laplace transformation of f of t. So you ignore that t to the t squared, when you're doing the f of s derivatives. So just a problem like that. Again, the thing about a lot of these problems is it's just going to come down to having the correct formula. So identifying which one is necessary, and then making sure you can do the correct manipulations when necessary as well.